So the next topic is the MEAR1 model, the MEAR measurement error autoregressive model. Bengt explained this yesterday. The ARMA 1.1 model, so the measurement error autoregressive model is this model where you have a single indicator for a factor at time t, for a factor, and and then you have an autoregressive equation for that factor. So it's a single indicator model, something that's not identified in general in standard SEM, but in this in this time series modeling, it's actually identified. Not only it's identified, it's basically equivalent to the most popular model in econometrics. Well, I mean, this is one of the most fundamental models in econometrics. So here's the ARMA 1.1 model. So it's you have mu, you're regressing this on the previous version of the that variable. So this is the AR part of the model. And then you have the residual, and you also have a regression on the previous version of the residual. And this model has 4 parameters, mu, phi, this parameter theta, and the variance of the residual. The measurement error model also has 4 parameters, mu and phi. And then you have the variance of the residual here and the variance of the residual here. So the two models are equivalent, and you can obtain the MEAR1 parameters from the ARMA 1.1 parameters using these 2 equations. You can do that as long as those 2 equations produce positive variances. So it turns out that the parameter space of the ARMA 1.1 model is a little bigger than the parameter space for the MEAR1 model. So it's not a one-to-one correspondence. This is slightly bigger. But generally speaking, in the data that we'll be interested in, this correspondence works well. One thing to note here is that the autocorrelation for the factor is always greater than the autocorrelation for the observed variable. So that's kind of a sort of a natural feature of this measurement error model, and you can once you start estimating these models, you will always have that the autoregressive parameter for the factor will be greater than the autocorrelation for the observed variable. And this model actually again shows that traditional SEM logic does not really hold well it doesn't hold in the DSEM framework. So one indicator factor model is perfectly identified. There's 2 reasons to prefer the MEAR1 model versus the ARMA 1.1 model. So we have in Mplus, it's a more efficient estimation for that model. The ARMA 1.1 model, as Bengt showed you yesterday, requires fixing of residuals to 0. You basically have to set up these residuals as factors, and then in addition to that, you have to introduce another factor with 0 variance. So the Mplus estimation of the MEAR1 model is more efficient. The MEAR1 model also, it's easier to interpret from a SEM perspective. So you have just measurement error, it's standard measurement error interpretations. There's 2 reasons to prefer the MEAR1 model against the AR1 model. So the MEAR model actually has more flexible. The AR1 model has an exponential decay of the autocorrelation. So if you have so the autocorrelation, so here's an example. So the autocorrelation function for the AR1 model, it kind of goes very rapidly down, and so it's somewhat unrealistic. Between the time periods, it goes quite quickly down because it's an exponential function. And for the MEAR1 models and the ARMA 1.1 model actually does not go exponentially down, so it can linger on for much longer. And essentially, it has 2 parameters. It's a 2-parameter function that matches the estimated autocorrelation against the observed autocorrelation function. So. But the reason actually I got obsessed with the MEAR1 model is because it actually resolves so many other issues. So there's actually not on this list, but we're going to see further on examples. So advantages of the MEAR1 model. So it resolves the issue about categorical data. So you can actually use time series modeling with categorical data as long as you stay in the MEAR framework. It resolves issues with covariates. So you can easily separate the covariate from the autoregressive part. It resolves these issues that I mentioned earlier with the stationarity of the model. You can easily transfer the trend in the model from outside of the autoregressive part of the model. So it's actually a framework that we use now all the time. So and you'll see all these examples in a minute. And it's very easy also to test the MEAR1 model versus the autoregressive AR1 model. You simply have to test that this variance here is significant. So here's a little simulation actually to put you in the right framework of mind when you think about these models. How easy is it to estimate an ARMA 1.1 model and a MEAR1 model? And this table is actually obtained in Mplus using the MEAR1 model, so it's the most efficient estimation that we have available. And here are basically the 4 parameters in this simulation study, and we're going to use sample size of, so this is a single level model, n equals 1. We're going to use sample size of 100, 200, 300, and 500. And you can see that even with 100, there's some bias in these parameter estimates. So keep this in mind, that this is actually the MEAR1 model has, it's not super straightforward to estimate. So it has these biases that, even you can see them for 200, for sample size 200, they're still there, although the standard errors actually now recovered. So the confidence interval gives proper coverage. So generally, to estimate an ARMA 1.1 model, if you talk to econometricians, they would generally recommend at least 100 and more like 200 time points to get good parameter estimates. Now, luckily for two-level models, which is most of our interest is for two-level models, this requirement for the time is actually is not needed because of the fact that we're not generally going to estimate those as individual specific for each cluster. So in a typical application, some of these parameters are going to be random and they're going to be cluster specific, but not all 4 of them. And the fact that some of the parameters are going to be invariant across the clusters allows you to carry information from one cluster to another, and therefore would allow you to reduce the demand for the number of time points in the estimation. And you would basically, you'll be able to get good parameter estimates even with 50 time points, and probably even less. Here's a little simulation study for ARMA 2.1 model. So here's the ARMA 2.1 model. It's kind of the ARMA 1.1 model, except now you the autoregressive part you can regress not just on the y from these previous time points, but also from the 2 periods back. And you also have this moving average part of the model. So regressing on, of course, the residuals here, and regressing also on the previous residual. So here's how you actually specify this in Mplus. This now is dealt with as a factor. So you basically use this to define this factor. And further on, you regress the y variable on the previous version of that factor. So this parameter is right here. And this is basically the autoregressive part of the model. And again, this is the one problematic issue here, is that you have to still further introduce a residual and then fix that residual to 0. And that's in the model of Monte Carlo, I can fix that to anything. But in the model statement, if I fix it to this very small value, then I'm going to cause this very slow convergence. So I fix it to 0.01. And let's look at the parameter estimates. In the parameter estimates in this simulation study, so I'm using a sample size of 500. And the parameter estimates are quite good, almost no bias anywhere. And the coverage is fairly good. So this is a more complicated model than the ARMA 1.1, and it's still fairly easy to estimate as long as the number of time points is sufficient. So let's see how some of the benefits of the MEAR1 model for categorical data. So we're going to be interested in basically actually estimating time series models for categorical data with just one categorical variable. Now, Bengt yesterday showed you, when you have multiple categorical indicators for a factor, That's a much easier situation. But this simulation kind of shows you that what I'm going to talk about here is using time series models with just one categorical variable. So univariate, and this actually turns out to be harder because with one categorical variable, you cannot measure, of course, the latent variable very well. It's a more unstable measurement model, but it's still possible to do that via the MEAR1 framework. So if you have a single binary variable, the MEAR1 model basically will be this. So this will be the between random intercept, and you have also this factor that's measured by the y star variable, by the underlying continuous variable, and then essentially you have the residual that's fixed to 1. And then this factor has its own autoregressive equation, and because of this equation, essentially you're building a model, a time series model for that binary variable. And with ordered polynomous variables, the same thing happens. You just have slightly different, the probability of this ordered polynomous variable being in a categories than just the difference between these probit functions evaluated at the different threshold values. But essentially, you have again the random intercept from the between level, and then you have this factor that essentially we're using from the MEAR1 model that's measured by the underlying continuous variable of the y. And then you have this, again, the autoregressive equation that actually is the essence of the time series model for the ordered polynomous variable. Just a couple of simulations here. So, I was interested to see what is the demand of the sample size here. And so what I found is that with binary variable, I needed 300 points to actually reduce the bias to get unbiased estimates. And now the coverage is a little low for these two parameters here, but if you run a much longer sequence, you'll probably be able to resolve this. Anyway, this simulation shows that even with just a single binary variable, you can actually estimate using the DSEM framework and this MEAR1 setup. You can use a time series model for a single binary variable. Binary variables are somewhat tricky because, essentially the information is being extracted every time there is a change from 0 to 1. And those changes have to be fairly often to provide some information for all these latent variables and parameters. So that works much better when you have more than one binary variable. You have multiple indicators for the same factor, and the factor is measured better. Or you can use ordered polynomous. When I redid that simulation with ordered polynomous variables, so I was able to, the demand on the time series is much smaller, so I was able to get good parameter estimates with 100 individuals measured at 100 time points. And you can see here the parameter estimates are fairly unbiased and the coverage is fairly good. Again, some low coverage here probably can be resolved by running a much longer MCMC sequence to get a more full posterior distribution.